Hi, I'm Andrew Bowman, a customer success engineer at Neo4j, and I'm going to talk a little bit about tuning Cypher queries. Now, for those of you on the Neo4j users Slack or the Neo4j community forums, you may have seen me lurking around the Cypher sections, helping out with Cypher questions and tuning issues. For those asking their questions on Stack Overflow, you might have seen me under my alias, Inverse Falcon. I'm also one of the primary authors of Cypher knowledge base articles for the Neo4j knowledge base. I've frequently been asked how you get good at writing and tuning Cypher queries, and I could probably distill it down to these. You need to have curiosity, patience, and flexibility as you tune, figuring out what the tuning is telling you. You need to know what your tools and resources are so you can effectively tune. You need to learn key principles of Cypher execution so you can avoid doing redundant work. And of course, you need practice. There's no substitute for that. The primary goal for all of this is to do less work, avoid redundant work in operations, cut out the work that's only going to be filtered out, and recognize cheaper ways to do what you want. So first of all, we need curiosity and patience. You're fighting against Cypher, or at least as you're ramping up. And sometimes you're facing the planner itself. It's also important to realize that sometimes when you're running into trouble, it's not necessarily the query that must change. Sometimes it means that you have to change your model. Sometimes you're running into something that Cypher isn't good with, so you need to fall back to APOC. And if that doesn't work, sometimes you might need to write a stored procedure. But first, let's talk about tuning tools and resources. You should have a browser window open with some reference documentation bookmarked. The Neo4j ref card, always good for looking up syntax. The official Cypher manual. The query tuning section in the Cypher manual is worth a read. It can cover some things that I'm not able to get to in these 30 minutes. There's a lot we can say about tuning that I won't be able to get to, unfortunately. And the section on execution plan descriptions. We're going to be reading over the query plan in the query planner, and we need to know what a lot of these operations will do. Query logs are going to be helpful, especially for finding queries already being used that need tuning. You can enable this in neo4j.conf for enterprise Neo4j. Successfully executing queries that exceed a timing threshold get logged, and if you turn on some additional configuration parameters, you can see some finer-grained timing breakdowns between planning, execution, waiting on locks. You check for page faults, page hits, bytes used, and help you out for interpreting what's going on in the query log. We have the query log analyzer, which is a graph app in Neo4j desktop. You point it to a query log file, and it will give you some aggregations, the counts of how many queries were executed, averages, min, max. Pretty useful. You need to know what's going on in your graph. So to view the graph structure, you can call db.schema or APOC metagraph. You need to see what indexes and constraints exist on your system. So call db.indexes or schema in the browser, prefixed with a colon. The counts store gives you some useful counts information. These are transactional counts, such as the number of nodes in your database, relationships, nodes of certain labels, relationships of certain types, and more. Now, this is the bread and butter of query tuning. Explain and profile. These produce query plans. You prefix the keyword before the query. Explain doesn't execute the query. It doesn't give you DB hits and only rough estimate of row counts. Profile, on the other hand, does execute the query. It includes valuable information such as DB hits and row counts. Explain is useful, by the way, because it can tell you kind of what's going on, and it can tell you how nodes are being looked up, starting nodes in the graph. We'll get to that a little later. So how do you interpret this? Well, we actually walk the tree by finding the upper leftmost node, so we'll keep on going left until we reach a leaf node. Load CSV is where we start. And then we'll move down until we reach a branch. And we've got the left-hand side of it, but we now need the right-hand side. So we'll move up one, and we'll once again go to the top and the left, to the nearest leaf node. It's a node by label scan on movies. This is a specific movie. We've got our left-hand side of this Cartesian product. The right-hand side is looking up a specific person. And we'll apply that and then repeat it as we go down until we reach our results. Cypher-shell also has profile and explain, but it looks very different. It's similar, except that it's inverted. We actually start producing results at the top, and our first operation is usually at the bottom. We'll follow this up until we reach a branch. We'll find the bottom leftmost leaf node, and then follow it through. db hits. You're going to see this when you profile queries. These are in red. You'll notice the more db hits, the more red there is. These are abstract units of db work. This is when we hit the graph, asking it something or writing something. Now, db hits are not comparable between operations. One db hit doesn't take constant time. And it's not always something that can be optimized. Sometimes all these db hits are required to get the correct result. Instead, consider it as smoke. There's not always fire there, but let it draw your attention. I tend to recommend looking at the rows. That can give you some good information as to what's going on. Rows are inputs to operations, and it multiplies out the operation, and the result are the db hits here. The more rows there are, the more work you're doing. That's key, remember that. Watch out for spikes in the number of rows. You can see we go from 44 to 200 and back to 38. That doesn't necessarily mean something is wrong, but it's possibly an opportunity to tune. Which brings us to key principles of Cypher execution. Topmost is row cardinality. This is where many people trip, whether it's enterprise customers or even journeymen or veterans. Operators produce results in records or rows, and we saw that in the last diagram. The key here is that operators execute for each input record or row. The implication is that the more rows there are, the more work is being done. So if you reduce the rows across the query, you reduce total work. The other implication is that matches are not independent, and that's a tripping point for our novice Cypher users. Little demonstration here. We're doing a profile. We match to the Matrix movie, we match to the directors of the Matrix movie, and we match to the actors who acted in the Matrix movie. By the way, there are 2 directors here, and there are 5 actors in our graph. This is the movies graph that you can play from the Neo4j browser. What we're getting as a return is the title of the movie, The Matrix, the collection of the distinct actor names, and the collection of the distinct director names. There should be 2 here and 5 actors here. So here's our query plan. 141 dB hits. It's very quick. So we probably don't need to tune, but we want to kind of show the principles here. Now, as mentioned, matches are not independent. Sometimes people see 2 matches, multiple matches following each other, and they think, well, okay, we match to the matrix, and then we fork out, and then one side matches to the directors, the other side matches to persons, and then magic happens, and somehow we get our results. But this isn't quite what happens. Matches are not independent. Remember, they execute per row that's generated from operations. So, in this case, we match to the matrix, we match to the directors, and this executes once. This produces 2 rows. For each of those rows, we are matching from the matrix to the actors. So we're doing this twice. The matrix is the same on both of these rows. We're doing double the work that we need to. This produces 10 rows. This is 2 of the directors times 5 of the actors to produce 10 rows, but we do get the right answer in the end because we're collecting by distinct properties here. Now this could be worse. If we went the other way around and went to the actors first, then this would produce 5 rows. And then for each of these 5 rows, we would match out to directors. That's 5 times the work that we really don't need to do. This produces 10 rows again. We're just multiplying it the other way around. We still get the same results, but we're paying a higher cost. By the way, if we think that we can get around this by putting it all into a single match here, this is just 1 match instead of 3, a longer pattern, with the matrix in the movie and directors on one side and actors on the other, this actually produces the exact same query plan. So what's going on here? What's increasing the cardinality? Matches and optional matches, especially if they're back-to-back, even if we separate them with widths, can increase the cardinality. You'll get this multiplicative effect between the number of results. When we do unwind, we increase the cardinality because for each element of the list, we emit a row. And procedure results, but only if they yield something. So what's the answer? How do we shrink the cardinality? How do we get around this? We can use aggregation. The grouping key, the non-aggregation variables, will become distinct. We can use the actual distinct keyword. Remember that this applies to the entire row, but not just a single variable. In special cases, we can use limit, but remember that this limits all rows, not the results per row. And if we just use width on its own, it doesn't shrink cardinality for you. You need to use one of these methods. So back to the query. How do we fix this? Well, we can note here that the problem actually exists between these matches. This emits 2 rows, and then the next match executes on both of them. So these collects are actually happening too late. This gets us the cardinality that we want, a single row. So let's move it up. Let's aggregate earlier. As soon as we match to directors, we'll collect them. And now we're back on a single row because the movie matrix becomes distinct, which means that when we match out to actors, that it's only done one time because we only have one input row. We'll collect the actors here, and we'll emit our results. We're at 101 total dB hits, so a nice little saving. We can also use a little trick called pattern comprehension, which was introduced in Neo4j 3.1. Now this looks a little bit weird, but we're using square brackets indicating that we're working with a list. We've got a match pattern in here, and we're extracting the dir variable here. So this is matching out from the matrix to the directors, and the directors are populating this list. Likewise for actors. It's like an optional match and collect. You'll notice that we start off at one row. This does the expansion outward, and this roll-up apply means that we're using a pattern comprehension. We're back to one row, and that's the input row for the second part of this, the second pattern comprehension. And we're at 94 dB hits, so some nice savings. Now some things are more expensive than others, and let's start with node lookup as we evaluate these. How do you find your starting node in the graph? In the examples we've seen so far, we've seen this node by label scan. This means we have to visit every node of a label. And if there are property predicates, we need to do some filtering on them. In this case, which of these movies is the matrix? We need to ask all of them. A label must be present in the pattern for this to be able to be used. Now the most expensive means of lookup, the one to avoid, is the all nodes scan. This visits every node in your graph, so the more nodes there are, regardless of label, the slower this is going to be. And this happens when we do not have any labels in our match pattern. If there are property predicates, we need to filter it. We ask all nodes in the graph for their properties, and we make sure that the title matches what we're looking for. Avoid these at all costs. The preferred lookup is node index seek, or some variation thereof, node unique index seek, for example, if we have a unique constraint. This looks up the node we want via an index. We need to create the index for this to work. It's used when there's a label and at least one property present. This actually looks very familiar to when I mentioned the node by label scan. The difference here is that we have created an index on movie title, and the planner can see, oh, we can take advantage of an index lookup. This is very fast. There are variations on how we can use this. We can use starts with predicates. We can see if a property is within a list. The fastest lookup is one you can rarely use, unfortunately. It's a node by ID seek. You look up via a graph ID. You need to know this ahead of time. Now, we don't really recommend using it. It's not a good idea to cache it outside of Neo4j, because what if the node was deleted? Now you have an ID that doesn't point to anything. Or worse, we do reuse IDs of deleted nodes. So maybe it's pointing to something else entirely. And that will ruin your query. We use this ID function here when we want to do this type of lookup. We also have something called a Fulltext schema index. I'm not going to talk too much about it, just you will use this when you're interested in doing case-insensitive string searching, or if you want to search over multiple labels or multiple properties at a time. And we can even create one of these on relationship properties. You call it via procedures, so it's not quite so easy to use as our regular schema indexes. Now, speaking of costs, there are costs for access and filtering of certain things, and properties are the most expensive. This is something to keep in mind. This is the way things are now. It's not necessarily how it's going to remain. We do have some improvements on the way. But property access, or filtering, is going to be a little bit more costly than the others. Doing filtering by node label is usually pretty good. Filtering by relationship type is fairly fast. Relationship type selection is also very fast, just because we have some supporting structures for this. But that's more of a modeling concern. We're not going to talk too much about it here. So, because properties are expensive, we need to find a way around that. And one of them is to just try not to use the properties until it'll have the least cost. So one of the ways to do that is to delay access until the node is distinct. Once we have our distinct node, then we can do property access. We can also do a collect here, and remember that the non-aggregation variables that form the grouping key become distinct, so this is effectively the same thing. We can wait until we filter or limit and have fewer rows. So if we have the matrix and its actors, we'll filter, or a movie and its actors, we'll wait until we filter out those that have less than 5 or less. And then we can do property access on the remainder. Or if we have a limit, we wait until we apply the limit, and for the remaining 10, now we can do property access, and it won't cost as much. If we need to use a property multiple times, it's actually a little bit more efficient to project it out. We can project out the title here. That way, when we use the title as the projected variable, we don't have to hit the graph each time. Sometimes it is a little bit more efficient to project before an expansion. So if movie is distinct at this point, we can project out the movie title before we expand out to the actors, especially if in our return we don't want to actually collect the actors. We want each actor name on its own row, and the movie will be the same per row. But we've just cheated a little bit because we've done the access when movie is distinct, rather than when there's multiple movies of the same type. If we're aggregating by a unique property, it's actually more efficient to aggregate by the node instead. So in this case, we're matching out from movies to the actors that were in that movie, and we'll collect those actors. And we could collect with respect to an ID property, for example, if this was unique. The problem here is that for each of those actors, say if they were 10, we'd have to do 10 projections of the ID property, 10 property accesses of the same movie before we do our collection. Whereas if instead we collect with respect to the node, in this case, now that the node has become distinct, we only have to do property access across one row. More efficient. There are times that we can move order by and limit operations up in the query. Many Cypher users who come from SQL tend to like to use limits in the return, but if you can move it up to where it makes sense as early in the query as possible, you can actually see some very nice improvements. So what we're doing here is we know that movie is distinct at this point, and we know that we're ordering by when the movie was released, and we're taking the top 10. So really, the point here is that after we've matched to our movies, we know that movie is distinct. We're not doing any filter operations. We have everything we need to do the order by and the limit here. And that way, we're only looking at 10 movies, and then the remainder of the work only applies on that 10, and not on rows that are only going to be filtered out because of the limit. While we're on the topic of order by, we actually have a neat feature called index-backed order by, which allows us to have an ordering operation, which allows us to hit the index and get the property from that, and avoid property access and the cost that it brings. Note the difference in the query plans here. The person name property is indexed, but the difference is that when we provide the hint as to the type of the name property, in this case an inequality saying that it's a text type, then it's able to leverage this feature. Notice that we don't have a projection operation here. We don't hit the properties store. We get it directly from the index, where it's already ordered. In certain types of queries, when we're interested in the count of certain degrees, but not so much interested in anything about the node at the other end, we can leverage something called degrees of relationships, as opposed to actually doing an expansion of the relationships to the node on the other side. The difference here, we match out a movie where someone has acted in it, and we use a count aggregation to get the degree. On the other query, we match to the movie, that's going to be a node by label scan, but we use the size function, and we pass a pattern here. And notice that the m variable is here, but there's nothing on the node at the other side. The only other thing present here is the direction and the type of the relationship. This is able to do get a node degree information from the node itself without doing any expansion and without changing cardinality. The point again for all of this is to aim to be lazy. Leverage node indexes for your starting nodes when possible, and use explain to double check that you're actually using the index lookup. Mind the cardinality, watch for those row spikes, and make sure that the high number of rows makes sense versus the counts that you see in the counts store. Get those rows down, aggregate early, use pattern comprehensions if you can, if you're collecting along the way. Be frugal with your property access. Go and strike when the cardinality is low. But what about practice? That was one of the bullet points, right? Alright, so next let's do a little practice with the Neo4j sandbox. So I'm using the sandbox, the Neo4j sandbox, the recommendations graph in this case. So here's our meta graph, and I've actually removed some of the node types here because we're only going to be looking at something very similar to the examples that we've been working with. Actors acted in movie, directors directed movies. There's no generic person label in this case. Epoch metastats gives us our counts. We've got about 32,000 node counts, 166,000 relationships, 9,000 movies, 18,000 actors, and 36,000 acted in relationships. Here's our schema. Now we have a uniqueness constraint on movie ID and on actor name. Those are the main ones we're going to be working with. So where's the query we need to tune? It's this one. This is kind of like a 7 degrees of separation, but from Keanu Reeves instead of Kevin Bacon. And we're going to movies and not other actors. There's a criteria here where all the movies that we match to can't have been acted in by Keanu Reeves. And for those movies that we get, matching out to their actors and their directors and collecting their names here per movie ID, which, as you recall, is unique. And we're ordering by that ID and taking the top 20. So it looks like we're timing out at 5 hops, about 1.5 seconds for 3 hops. Now the first thing that's jumping out at me just looking at the query plan is this is a node by label scan on movie. It's starting here. It should be starting at Keanu Reeves. We're missing his label. That should allow us to do an index seek. There it is, node unique index seek. And we're already at 19 milliseconds here. So we can probably scale up here. 6 hops. We're still under a second. How about 7? Can we reach that? Still have some trouble. So there's more to tune. So what else can we do here? I'm noticing a lot of these movie labels here. That seems a little redundant. This is the same movie. Why do we have to keep on filtering on the label? This isn't going to buy us much, but it'll make things less confusing. Usually when there's a label involved, that means it's something new that we're introducing. Alright, that looks a little better. I don't think we're going to get too much out of it. That's right, that's still the 7 hops. Okay, moving on, what else can we do? Got this massive var length expansion, 39,000 rows, but I know we don't have that many movies. We ought to get distinct movies from this instead. There we go. So we're at to 7, and we're at about 500 milliseconds. So that was a really nice boost. Okay, what's next? You can see some heavy dB hits here. What's this? Well, that's our acted collecting the actors. And over here, that's 105,000 dB hits. And this is a section where we need to make sure that Keanu Reeves did not act in these nodes. That's a lot of dB hits. We probably don't need to do that much. We don't actually need to expand this out. Why don't we collect the movies Keanu Reeves has acted in? We're going to use that to do our filtering here. So rather than hitting the graph to expand, we're just going to do some list membership checking. All right, a little bit. 400 milliseconds. Okay. We've got this limit here. We're ordering by ID. We're aggregating on this unique property. This is something that can be moved up. Once we expand out to movies, we make sure that that movie is one that Keanu has not acted in. We've got what we want. That should allow us to limit much earlier. Oh, there we go. All right, 87 milliseconds, around that area. What next? Well, we can do something about this. Now, well, we've got these back-to-back matches, and we can use pattern comprehension for them. It probably won't get us too much, because there's usually only one director per movie, not too many with multiple. But let's add that in anyway. That's nice. So we don't have to expand out and we don't have to collect by it. 138. We're still in the neighborhood of about 80 milliseconds or so. At the moment, that's probably all we're going to get.